In a prior video, I explained how general relativity works and what the math of Einstein's field equation is trying to say. These are some of the most proven equations in science, but we've found that quantum mechanics, which is at least as proven, ruins them. For example, if you consider the simplest atom, the hydrogen atom, consisting of one proton and one electron, quantum theory says that the electron is in a superposition. This means that it is in multiple locations at various distances from the nucleus at the same time. We only know the probability of finding it at a particular radius if we were to measure it. This is a problem because since the electron has mass, according to general relativity, it must curve space-time. But if it is in multiple locations at the same time, then where is the curvature? Is it also at multiple locations at the same time? There is no such thing as superposition in general relativity. Another problem occurs in the case of black holes. There's a region of space called the singularity, where matter and energy is supposedly compressed to an infinitely small point with infinite curvature of space-time. But the equations of general relativity treat space-time mathematically as being flat at infinitesimally small distances and then calculate the overall curvature based on this presumption. This does not work at the singularity because infinite curvature at an infinitely small point results in nonsense results in the math of general relativity. So the question is there any way we can reconcile these two highly proven theories so that we can have a true picture of how reality works? Well, there are two theories that attempt to tackle this reconciliation: loop quantum gravity and string theory. The explanation of how these two theories work is coming up right now. Before I get into loop quantum gravity and string theory, let me tell you what inspired me to do this video. I recently watched a 2-episode documentary on Magellan TV, today's sponsor, called The Amazing World of Gravity. It's hosted by one of my favorite educators, Jim Al-Khalili, and it's in 4K. Magellan is a new type of streaming documentary service founded by filmmakers and producers who bring you great premium documentary content. Featured subjects include history, nature, and my favorites, science and space. You can watch it on any of your devices as well as your TV anytime without any ads, and they have a huge library of 4K content. Magellan TV has a special offer right now for Arvin Ash viewers. If you use the link in the description, you'll get a free 1-month trial. I highly recommend Magellan TV, but be sure to use the link in the description. The best and most accurate theory of the nature of reality is represented by the standard model of particle physics. This is like the periodic table of chemistry, except it's for fundamental particles. Although this looks fairly simple, it is really a visual representation of many equations that are behind it. Here's a glimpse of what those equations look like. I want to draw your attention to the red gauge bosons on the chart. These represent the fundamental particles responsible for 3 of the 4 known forces in the universe. The gluon is responsible for the strong force, the photon is responsible for electromagnetism, and the W and Z bosons are responsible for the weak nuclear force. The way a force is conferred is through the exchange of virtual bosons. So for example, in electromagnetism, an exchange of virtual photons results in an exchange of momentum, which results in 2 like charges repelling each other. Attraction happens through the exchange of negative momentum, similar to this boomerang analogy. I made a video recently on how these forces work at the subatomic level if you're interested in viewing it. You'll notice that one force is conspicuously missing from this picture, and that is gravity. This is because according to our best model for gravity, Einstein's general relativity, gravity is not a force, but is a result of the curvature of the background, the curvature of space-time. But the equations of general relativity treat space-time as a bending of the continuous background of space-time, not as a result of discrete particles that confer a force. This is a problem. Stars and planets are made of molecules, atoms, and radiation. These are ultimately made up of elementary particles of the standard model. And we know that these are made up of discrete units of energy. And the forces that hold the atoms together are also due to discrete units of virtual particles represented by the gauge bosons. And it's the exchange or swapping of these virtual bosons that holds and breaks up atoms and molecules. The universe is bumpy. There's no such thing as continuous matter and energy. This is why Einstein's general relativity is a problem. Why should reality have 2 sets of rules? Quantum mechanics for the very small and general relativity for the very large. Even if they appear to follow two separate rules, they should unite at some fundamental level. One set of laws should emerge from the other because we live in one reality, not two different realities. This is partly the reason that most physicists believe general relativity is incomplete. You could ask, well, why can't quantum mechanics be the one that is incomplete? Here's part of the reason. Of the four fundamental forces, three have very robust theories rooted in quantum mechanics. Only gravity lacks a quantum description. Not only the forces, but also the vast majority of particles, including atoms and molecules, have very robust quantum theories explaining them. Quantum mechanics also has almost all of the classical physics within its limits. On the other hand, classical physics, like that of general relativity, does not include any quantum effects. We came up with quantum theories because classical physics did not work under all circumstances, and it could explain more observations. What we've learned in the past 90 years is that quantum physics is the fundamental language of reality. This is why it is thought that gravity needs to be brought into the fold and not the other way around. Now, one way to do this is to hypothesize that perhaps the background, space-time itself, is quantized. This is what loop quantum gravity, or LQG, attempts to do. It attempts to show that the fabric of space-time is not continuous, as Einstein presumed, but is itself made up of discrete quanta. Think of a TV screen. Even an HD TV at its smallest level is made up of discrete pixels, which cannot be further reduced. This is different from every other theory, including string theory, because even in string theory, space is the background or canvas on which strings vibrate. In LQG, this space-time background is itself quantized, like your television. So this means that distance has a minimum quantity, about equivalent to the Planck length, or 10 to the negative 35 meters. Similarly, area has a minimum value of 10 to the negative 70 meters squared, and volume has a minimum value of around 10 to the negative 105 meters cubed, below which it cannot go. This is super tiny. To give you an idea of the smallness of the scales we're talking about, LQG says that there are about 10 to the 99 quanta of volume in every cubic centimeter of space. This quantum of volume is so tiny that there are more such quanta in a cubic centimeter than there are cubic centimeters in the entire visible universe. And time itself has a minimum quantity as well, which is about 10 to the negative 43 seconds, or close to Planck time. And what do these space-time quanta look like? Well, space-time is basically made up of finite loops with nodes connecting them. The nodes that intersect is where the quanta volume of space reside. It has a volume that is a multiple of the Planck volume, 10 to the negative 99 cubic centimeters. The loops in between these nodes represent two-dimensional areas, and large quantities of these loops and nodes are called spin networks because their properties are related to a particle quality called spin. Space is defined by the geometry of the spin network, and time is defined by the moves that rearrange the spin network. The spin network, when combined with these quantum movements of time, is called a spin foam. Time does not flow like a river in the spin foam, it ticks like a digital clock. And each quantum tick or movement of the spin network is about 10 to the negative 43 seconds. Every location in the spin network where a quantum move takes place, time has ticked once. How do particles traverse this quantized space? When mass and energy are added to the spin foam, the shape of the volumes of the spin network is distorted. This distorts space and time because any movement of these quanta also affects the time quanta. Time is essentially movement of these volume quanta. And this distortion of space and time is what we perceive as gravity. The exciting thing about LQG is that it makes some predictions that could be tested. For example, it predicts that the speed of light has a small dependence on energy. Photons of high energy travel slightly slower than low energy photons. The effect is very small, but it amplifies over time. So two photons produced by a gamma ray burst, for example, billions of years ago, if they are of different frequency, should arrive on Earth at slightly different times. And this time delay should be large enough to be detected by our instruments. But sadly, This has not been observed. It is possible that either the theory is wrong or our instruments are not sensitive enough. A second way to quantize gravity is to theorize a completely new framework of reality based on a new understanding of fundamental particles. This is what string theory attempts to do. In string theory, the fundamental particles of the Standard Model are replaced by something even more fundamental, one-dimensional fiber-like strings. The simple change of treating point-like particles as one-dimensional string-like particles makes a huge difference in the mathematics. Now, if you take those strings and show that they can vibrate, it turns out that different types of strings with different vibrations behave just like the elementary particles of the Standard Model. So the various particles of the Standard Model can now be simplified by replacing them with fundamental strings. Now, this sounds great, but one of the biggest problems is that these strings would need to vibrate not just in the 3 spatial dimensions that we're used to, but in at least 6 more spatial dimensions in order to mathematically account for the various particles that we know of. So the question is, where are these extra dimensions? It does not appear that additional large dimensions in our universe exist. So physicists speculate that these dimensions could be very small and hidden from our perceptions. This is analogous to the way that a rug appears smooth from a distance, but if you look closely, you'll see small loops and fibers in its structure. Strings vibrating in different dimensions is analogous to the way that a wind instrument can make different sounds depending on the way the air flows through its various surfaces. This is similar to the way that the same string can take on different properties when vibrating in different combinations of dimensions. Strings can be open strings or closed strings. The interesting thing is that if you treat the universe as strings vibrating in 9 dimensions, a particular closed string vibration results in a unique graviton particle. This appears naturally in the mathematics of string theory, so this would allow for the existence of a force-carrying particle just like the force-carrying particles of the other 3 forces. Similarly, particular sets of strings and vibrations could account for the quarks, and particular vibrations in specific dimensions could account for different color charges of the quarks, red, blue, and green. So for example, we could have 2 up quarks of different colors and 1 down quark of a third color. This would be a proton, since they're made up of 2 up quarks and 1 down quark. Note that the 6-dimensional Calabi-Yau manifold depicted here as a 3D-like structure is for illustration purposes only. The 6 small spatial dimensions are not something that we can imagine with our 3-dimensional minds. The actual structure of this manifold and the vibrations within it is not something that can be visualized, particularly if you add the dimension of time to this picture. The promise of string theory is that most, if not all, of the fundamental constants could come out of it. In addition, all the charges and properties of fundamental particles could emerge. This would be huge. It would be a true theory of everything. It's ambitious, but it also has some problems, the most obvious of which is the idea of 9 spatial dimensions. Some scientists have attempted to detect this, for example, by creating microscopic black holes at the Large Hadron Collider. The idea being that if gravity is being diluted due to 9 spatial dimensions, then creating black holes on very tiny scales in only the smaller 6 dimensions may require a lot less energy than in the same 6 plus our 3 larger dimensions. But so far, no small dimensions have been detected in this or other experiments. The other problem is that superstring theory requires the existence of supersymmetry. This is the idea that each particle of the Standard Model has a shadow partner particle with different masses. The problem is that in a decade of searching for them at the Large Hadron Collider, no trace of supersymmetric particles has been found. String theory probably won't work without it. The reason that quantum gravity is such a difficult problem to solve is partly because gravity is so incredibly weak. For example, it is 10 to the 39 times weaker than electromagnetism. This is why a magnet can easily pick up another magnet against the pull of the entire Earth. We may never be able to detect the effect of gravity, for example, between an electron and a proton inside a hydrogen atom. It will be completely overwhelmed with the electromagnetic force between them. Quantum gravity predictions may be impossible to test. We may likely have to verify it through other predictions that such a theory makes. Any theoretical formulation is almost certainly going to be driven by thought experiments rather than real experiments. Loop quantum gravity is inspired by Einstein's idea of treating gravity not as a force, but as the curvature of the background. It just quantizes this background, but it largely ignores the other forces. This is why it's not currently a theory of everything, but a theory of quantum gravity. It's not clear that it can incorporate the other forces or particles of the standard model. On the other hand, string theory is inspired by the standard model, but introduces a completely new mathematical formulation which attempts to bring gravity along with everything else into the fold. But it assumes that space and time already exists and does not attempt to create them. So in that sense, the nature of the background, the space and time, is not something the string theory can answer. So neither theory at this point is well developed enough to be a satisfying theory of quantum gravity, let alone an all-encompassing theory of everything. Now, what if these two theories could be combined together? That could be exciting, and some researchers are working on this very idea. So that could be the next big thing. Or of course, all this could be wrong, but we won't know that until the next Einstein comes along and shows us mortals how the universe actually works. I'd like to thank my generous supporters on Patreon and YouTube. If you like my videos, consider joining them. And if you have a question, leave it in the comments below, and I will try to answer it. I will see you in the next video, my friend.